about something. If you see something that's wrong, or if you think that we're missing some information, or anything is, you know, implying something that's not true, please point it out to us. Also, if you go down to the bottom, you can select any blank row and right-click and comment there and submit questions that you have that you know, you think that would be good to answer here. It's really meant for, like I said, little knowledge bits. Some of them get a little bit lengthy, like this one, but for the most part, they're fairly short. And I'd really like you guys to read through it, and you might it might inspire you to look into something else that you hadn't really considered yet. So please join us. I'd like this to be hundreds of questions, and the intent is to provide it eventually in some kind of a better web consumable fashion that's accessible to everybody and you know, easily browsable. By the way, you can go up here and click. I added this topic column here, since that's new since last time. That's a good field to sort on if you're looking for particular things that that you might want to, you know, just look alphabetically on. And if you're in this view, by the way, these little links about, well, this question was answered in this other topic, they point to the wrong place now. Once you're in this little filter view, you got to click this thing off, close that thing, and then those links work. I don't know why, but for some reason, Google Sheets doesn't update the links there. They become absolute instead of relative when it's sorted. But anyway, that's all.
Thanks, Jeff.
You're welcome.
And after John is talking today, I think that Stephen Rocco is going to share some of the Hub 75 progress. Is that accurate, Stephen? Okay, cool. All right. Because I saw a picture of 6 panels and it looked like everything was in order, and that was really neat. And if there are any other topics that want to be discussed when John is done, just bring them up, because we'll just let this meeting go as long as it needs to go. Well, live from Hollywood, California, JonnyMac.
Unmute myself. Hello, everybody. Good to be back. Very happy about this. I'm hoping that, first off, thanks everybody for coming. This is a nice crowd today, I think. And what I know that not everybody has, you know, one of these or any particular transmitter, but I think you'll still find today useful, because we're going to talk about serial communications with the Propeller too. And yes, we've got serial objects, but the serial that we're going to be dealing with in SBUS has a couple of particular things that you might encounter elsewhere. So going through today, I'm hoping it will prepare you for other devices that you encounter in the past. So let me share my screen. And so those of you that did buy the, are you able to see my screen now? And I'm pointing to the the forums. Bueller?
Yes, JonnyMac.
Yeah. Right. Okay, good. All right. So if you haven't yet configured your FLYSKY transmitter, this video that I posted is one of the better that I found. Stephen and I were talking a little earlier. The user interface for configuration is not difficult, but it's a little inconsistent. Once you see this video, then the document that I attached a specific PDF where the way I do things, which are mostly out of this guy's video. You'll want to set that up because the FLYSKY defaults to its own serial protocol out of the receiver. You need to go in and configure the transmitter to tell the receiver to output SBUS, which is what we're using. Now, the reason for selecting SBUS over iBus is SBUS is kind of the standard in the industry. It was created by Futaba, and as you know, Roy has a receiver already that's not a FLYSKY, but it does SBUS. I have a friend, many of you know who he is, Rick Gallinson, who works in the TV industry. He couldn't be here today. I asked him because he's busy working on Star Wars TV shows. And a lot of the work that he does in puppeteering characters and robots and other stuff on set, they end up using a transmitter that goes into a receiver. SBUS comes out and goes into a microcontroller. I've written the SBUS receiver for the P2 and the P1, so he has the opportunity to use it on both sides. So hopefully we'll get some more Propeller code into the Star Wars universe. Okay, so do that. I also, for those of you that downloaded code, I don't know if you noticed, I uploaded everything last night, but I added a secondary file today, a bonus file. The reason for that is since Spin 2 is still new to a lot of people, and we're talking about writing objects in the transmit part of the project today. We're doing an object that runs in its own cog, but it's a spin cog. And one of the questions that comes up over and over and over with spin cogs is, how big do I make the stack for the spin cog? So we're going to talk about that. And the little bonus program shows you a mechanism that I use that I learned from Phil Pilgrim probably 10 years ago on how to figure out an appropriate amount of space to stick into the, to define the stack for. Okay. Any questions before I start the gory stuff? Okay, remember the rules. You ask me a question, I'll give you an answer. If I ask you a question, you give me an answer. It's easy, right?
And if you're afraid to ask a question, you can type a question.
Or that too, yeah.
Some people might not even know what we're talking about today because there are a lot of new names.
There are new, and but that's really good. So we'll give a very big overview.
And so they might be here for like a Raspberry Pi seminar or a Pico seminar, who knows what.
Well, that's okay, because I'm going to talk about the algorithms used in SBUS, and I'm coding it in Spin and PASM.
For the Propeller 2.
For the Propeller 2. The code, though, the algorithm is very tidy. And, you know, somebody like Roy, for example, who's a master C programmer, he could convert the Spin code to C in probably less time than it takes me to explain what it's doing. It's very, very simple once you kind of get the hang of the algorithm. So we're going to spend a little bit of time on the internal machinations, because once we understand that, everything becomes very easy. Then specifically, we're going to deal with how the Propeller 2 handles serial in and out, and how we can take advantage of smart pins to do the heavy lifting for us. So today we're talking about, and I should ask, are everybody seeing my presentation screen, my PowerPoint?
Can I ask you a quick question, John?
Yes, Greg. Sure, go ahead.
My unit, when I'm trying to follow the configuration here, and on the output, I have PWM and PPM, but I don't see anything about that in the document.
Oh, because we don't care. We're not using that. So the PPM or PWM are for other devices. If you press OK, there should be a little box around that.
Okay, it jumped over. I got it now.
Yeah, press OK to move to the next box. This is where those goofy interface things, and then select up or down so you have.
Yeah, I got it now. I got it now. I was trying to figure out how to get past it. I thought I had to select it before.
Oh, no. The key thing, I'll tell everybody, just a key thing to remember with this. When you have a value changed to what you want, in order to save it, this is not intuitive, you have to press and hold the cancel button. So press and hold the cancel button for a second or so, and then it will exit back to the next highest menu, and you'll know it's saved. Now, you know, the guy in the video recommends once it does that, click on OK again to get you back into that selection, and you should see your save change. So that's one of those weird quirks. I mean, there's not a lot of interface on here. So, you know, I guess they've done the best they can. Once you get used to it, as I was speaking with Stephen earlier, once you've done it a couple of times, it's not bad. Okay, so let's talk about SBUS. And I do want to say, you know, this started for me a couple of months ago because I have a couple of really close friends, Rick, as I mentioned earlier, And my friend John Huffman, who owns Johnny Jib, who are both associated with show business and both need SBUS. Rick primarily needs SBUS receive. John needs SBUS transmit because one of the products that he has uses a mechanism that's built by another company that does pan, tilt, and roll for a camera. It's a gimbal, and it takes SBUS to command it. So what he wants to do is take that and control that with a propeller, and then also run controls to the lens on the camera, so that he has full aspect of the orientation of the camera and the focus and the zoom, and all of that is going long distance over an XB connection, something he and I've done many times. So I need both sides of this, and we're going to talk about that today. When I started this process, of course, like anyone, I went out to the internet and did some research, and there was a lot of confusing information about SBUS. I'm going to say that I'm taking the tack that we're coming from the electronics point of view, not the RC world's point of view. Because the thing that confused me initially with the videos I was watching is that people were saying that SBUS uses standard serial. You're going to find it doesn't from the electronics point of view. So again, all of my framework is from the generic microcontroller view of serial, because this is straight up serial. There's nothing magical about it. It is a protocol over standardized serial. It's not like one wire or like you know, the WS2812. It's not a specialty thing. It's generic serial. We just need to learn how to deal with it. So Futaba created this, and there's two versions now. There's SBUS, which we're going to deal with, and there's SBUS 2, which is bidirectional, so that they can add telemetry to planes. You'll notice on the receiver that comes with your FLYSKY, it has two connections, because the iBus allows you to do input, so you can connect external devices. Down the road, I will write an iBus object for the P2 as well, and see if we can get back telemetry that we can display on the screen. That's a future project. But just be aware, there's SBUS and SBUS 2. We're dealing with SBUS 1. Now, Futaba never published a protocol. This was sorted out by people like us, you know, that hook up a logic analyzer, a scope, and look at it and figure it all out. So there is no official protocol that you can find. Of course, I went looking for that too and ran into a roadblock. Luckily, the specification is well known for SBUS and very easy, and really easy for us to implement in the Propeller, P1 or P2, particularly the P2 though. So SBUS is serial data that runs at 100 kbaud, a little bit unusual vis-a-vis, you know, PC, you know, baud rates, but you know, nothing that we can't handle. It is 8E2, which people that haven't done a lot of serial may be unfamiliar with, and it is inverted, something people that haven't done a lot of serial may not have dealt with. So we're going to get into all of those details. But this means we have 8 data bits. We're going to have an even parity bit, and we're going to use 2 stop bits. That's the idle time between bytes in a packet. And inverted means our voltages are going to be opposite what we would normally have on a true mode serial line. SBUS is a constant set of frames that are going out. That each frame is 25 bytes. There is a header byte that is 0F and a footer byte that is 00. There's no checksum or anything like that in the packet. So error checking is very minimalistic. You'll see in the code, we look to make sure the header and footer are correct. And we are also checking parity, you know, for each byte that is coming in. But there's no checksum in the packet. So it could be that the decision was made, well, we're sending this out every 7.5-ish milliseconds. So if there's a problem, we'll correct really quickly. That I don't know if that's the case, but that's logically what could happen. So if you look at the frame, again, I just mentioned there is a header byte that's 0F. There are 22 data bytes. There is a flags byte and then the footer. Now, the channel values from the transmitter are 11 bits. So what we're going to do is we're going to encode 16 channel values into 22 bytes. The reason for that, again, I'm speculating because we don't have a spec or any, I wasn't able to find any information from Futaba that talked about why they did what they did. But if you have 11-bit values, there's no need to use 16 bytes to transmit them. You know, that's wasting 5 bits. And so what you're going to see is we encode or we pack those values into 16 11-bit values into 22 8-bit bytes. Now there are 2 more channels. So there, in the SBUS world, there are 18 total channels, but the last 2, channels 17 and 18, are just bits. So they're either on or off. And those are transmitted in the flags byte. Okay, so pretty easy. Again, SBUS is a packet of 25 bytes or frame, we call it. And from byte 1 to 22, that's going to contain our variable channel values. And then in the flags byte, which is byte 23, we're going to grab 2 bits out of there that are our last 2 values. So we're going to call them digital. They're switched. They can only have 2 values. The other ones can have anything in between. Any questions so far? All right. And here is the makeup of that flags byte. Only 4 bits are used. Bit 0 is for channel 17. Bit 1 is for channel 18. Bit 2 is a lost frame bit. So if the transmitter shuts down or something happened, it will we'll get an output that says, hey, the data that I sent you is actually a repeat of what I sent last because I lost the transmitter. If the transmitter stays lost for a certain amount of time and you've configured the radio for this, it will set a fail-safe flag. So for example, the standard, as I understand it and how I used it in here, the standard fail-safe is to take the throttle channel, which is the left stick up and down. On this device, it's not sprung. The default fail-safe mode is that to off. So the idea being if you're flying an airplane and your transmitter shuts down or it gets out of range, the throttle will be killed and hopefully the airplane will glide to a happy landing. That's what fail-safe does. In this configuration, you can set up fail-safe any way you like. The standard for RC flyers is to kill the throttle channel, leave everything else as it was. But those are the 4 bits that we will deal with in that byte. Okay. All right, let's talk about serial. So we'll do a quick serial review. Many of you, this is old information, but I want to cover this to make sure that we're all on the same page, especially for the new people. And we're talking about asynchronous TTL serial. So this is asynchronous means we have an agreed upon bit rate, or we call it a baud rate between devices. So the transmitter is going to send out data at a given bit rate or baud. The receiver has to be configured for that same bit rate. Otherwise there will be a problem. In a traditional kind of setup, we call it true mode. The idle state of the transmit line is high. So in our case, this will be 3.3 volts. When we want to send a byte, we're going to pull the line to ground and we're going to wait 1 bit period. This is called the start bit. This gets everything going. The next 8 bit periods we will set the transmit line to the level of the bit. Notice too, the bit order is LSB first. So bit 0 goes, then bit 1, then bit 2, etc., all the way through bit 7. So we're in standard serial, we transmit the bits from 0 to 7. And in true mode, the level is the value of the bit. So in this case, bit 0 is 0, bit 1 is 0, bit 2 is a 1, so the line goes back high, etc. Now, after we've sent the 7 bits, we're going to return the transmit line to the idle state, which in our case is high, for at least 1 bit period. This is called the stop bit. Okay, we need this time in between bytes so that what we just collected we can store somewhere. Now, this byte that I just showed you, this is what you see all the time. And you, if you didn't know what this means, now you will. This is 8 and 1. So it's 8 data bits. There's no parity bit, and we have 1 stop bit. So again, 8, no parity, and 1 stop bit. Now that'll, the reason I'm emphasizing that will become clear in the next slide. We can invert that. If we do, the idle state now is at ground, and we go high for our start bit. We send out the bits in the same order, but we're going to set the transmit line to the opposite state of the bit. That's why there's this bar over that. That means an inversion. So you'll notice that from here to here, this is just a mirror. This is the same value. If you, when transmit and receive in these modes, you'll get the same value on the end. It's just that we electrically have done it differently. Okay, but notice what we have to do with the bits, though. We have to flip their values before you transmit them. Okay, this is inverted mode. SBUS uses inverted mode. There are some widgets you'll find that use inverted mode. Back when we used to have PCs that had 9-pin serial connectors, this was very popular because the RS-232 level serial would work out such that if you put a diode and a resistor in there, you would get inverted serial, and you could go right from your PC into a basic stamp or another small processor. Okay. All right. Here is a scope capture of an SBUS byte. So you can see this is inverted mode. We're starting low, and then you can see that the edge, the triggering is set to go high on an edge. So here we go high, and then we do our bits. So if you look very carefully at this, we have 0, 0, 0, 0 in electrically, but that's actually going to be 1, 1, 1, 1 from a data standpoint. The same happens here, although we have all these highs, so they're actually going to be flipped to 0. Now this bit here is the parity bit. So in SBUS, we're going to send the 8 data bits, and then we have this extra bit, this parity bit. What we're going to do, the way we're going to set that, you remember we said it was 8E2. That E means even parity. So what we're going to want to do before we transmit anything is count up the number of ones we have in our byte. And if it's even, we leave the parity bit alone. We leave it at 0. If it's an odd number of bits, we're going to set the parity bit to 1. The idea is we're going to transmit an even number of ones in our packet. Now you see at the end, we have 2 bits low here. These are our stop bits. That's here's a start bit, here's 8 data bits, here's even parity, and here's 2 stop bits. So this is our 8E2. This is a scope capture so that you can see that. The value of this, when we read in the stream, is 0F. And you can see, remember, this is bit 0 here, and this is bit 7. So this is 11111, 0000. Remember, and they're flipped over, so that's 0F. So that's what, if you hook up a scope or a logic analyzer, you're going to see something that looks like that. It's a little easier to see here. This is the SBUS header byte. This is just a little cleaner and easier to see. So here's our start, our bits, our parity follows that, and 2 stop bits. Okay. Now this, you notice that we have 1, 2, 3, 4. These are going to be ones in our original byte. So the parity bit will be 0. Since that gets inverted, it's high here. Here we'll look at another byte. In this case, we have 1, 2, 3 ones that are part of the data byte. So the parity has to be set to 1, and in inverted mode, that will flip to 0. So that is what's going on with that parity bit. One of the things that I noticed when I was looking at what other people were doing with SBUS is most people simply ignored the parity bit. I don't in my code. It's very easy to deal with. And that way, if we have a packet and we get a parity error, we can just we can set the frame loss flag and tell the propeller, hey, we dropped the frame. So be wary. Okay, questions? Okay, maybe this won't take 2 hours.
I got one question. I can't see. I have a 6-channel receiver that came with mine, and it looks like yours is a 10.
I did get a 10-channel receiver, but it doesn't matter. As long as you have 10 channels on your transmitter, you do have to tell it to use all 10 channels. By default, the FS-i6X is configured for 6 channels. You do have to go in and tell it you want to use 10. That way the switches will become active.
Okay.
In the default configuration, it uses the sticks and the 2 knobs here.
Okay.
By setting it to 10 channels, you get these auxiliary switches.
Gotcha.
In the chat window, Dennis posted a link to how to set it up for 10 channels.
Yeah.
Okay, good. Yeah, and it's in my document too, I believe.
Does anybody know what the power configuration is on that 6-channel receiver? The manual that I have is written in Chinese.
I did post a link to the other one. Are you talking about how to get power into the receiver?
Yes.
If you look on that, Greg, on that page that I posted, well, if you look at your receiver, now I am looking at the 10. Hopefully yours is the same. There are a bunch of vertical 3-pin headers. Those are the servo channels. Above that are 2 horizontal headers.
Right.
And you'll notice looking at the top of the receiver, it says iBus, and then on one side it says sense, on the other side it says servo.
Right.
Okay, so on my the pin underneath, so the one I'm using, the one called servo, because remember this is going to our SBUS output.
Oh, never mind. I see what the problem is. I got the jumper off for the 5 volts on the headers.
Okay, that'll do it too.
Noticed that. That's why it's not lighting.
When in doubt, give it some power.
Hey, John, I have a question.
Yes, sir.
There we go. Now we got power.
Is there a way to exploit the transmitter to just transmit, like you serially feed it these data packets and have it do the radio transmission for you? Or can packets only originate from the controls on the radio?
There are other transmitter devices that use, whatever is going on in this, because it's a 2.4 gigahertz transmitter and receiver. There may be data, transmitters available that would let us say, which would be really interesting, because I think I know what you're getting at. We could create our own transmitter or our own controller with the P2, especially giving all the analog capabilities. But at least on this device, I don't know of any way other than opening it up and hacking it to get data onto that packet.
Okay, thanks.
Okay. Now, remember, we were getting back to these bytes, and I'm getting into the gory details of this because we have to suss all this stuff out in the packets. We're looking at 1 byte at a time. Here is a capture using a logic analyzer of an entire frame. Now, I added the blue lines to this image so that you can, you can distinguish the individual bytes. But that you should see. Let me see if I can zoom in on here. Oops. Here's that first byte, and that shape should look familiar, right? It's this. Oh, that zooming thing's being problematic. So this is our start byte, and you can see it right here. Same thing. And here are the first 22 bytes. Are the 16 channel values that are encoded together. The 24th frame, or byte 23 in the packet, is the flags, and the final frame is 0. So this is what the entire frame looks like. At 100 kbaud with 25 bytes, it takes about 3 milliseconds to transmit the entire frame. At least with the way that the FLYSKY is set up and what I've measured, it repeats that every 7.8-ish milliseconds. So a little less than 8 milliseconds, every 8 milliseconds, it's transmitting a new frame. So that allows you to update things really quickly. And finally, this is what I was talking about earlier. You can, with PulseView, set up a decoder. And, you know, so I told it, hey, this is serial and it's inverted and it has even parity. And so you can see, here's our start byte. It was interesting. I actually thought this was an error. Notice how it says parity bit and it's red. Red normally means there's a problem. But when I went to the decoder and I just, to see what would happen, I set it to odd parity. This changes to parity error. So this is correct. Here's our 8 data bits, and you can see underneath, this is a 1, this is a 1, this is a 1, because in the serial decoder, you can tell it, hey, it's inverted data. And so you see all that. So that was a very happy thing about, again, piece of freeware with a really inexpensive logic analyzer. I could verify everything, especially with the transmit. As I was saying earlier, I don't have an SBUS servo right now. So what I did was I used my logic analyzer to look at the output from the propeller to make sure I was doing everything correctly, and I could see it here with the protocol analyzer. Okay, any questions on serial? Everybody comfortable with serial? Again, we're doing inverted serial, which means we start low and we go high for a start bit. Our bits are inverted. After the data bits, we're going to have a parity bit, and that's going to be configured before the inversion so that there is an even number of ones in the data packet. That doesn't count the start and stop bits. It's just within those 9 bits, we're going to have an even number of ones. And then we have 2 stop bits. Okay. All right. Here's where we get into the really, the gnarly stuff, but it's not too hard. As I was saying a minute ago, the values for the, you know, the sticks and the knobs, they're 11 bits, but we're transmitting 8-bit values. So we have to do something about that. Now, again, we could have used 2 bytes per channel, but that would waste 5 bits for every channel, and that would take more time. This is not a really very fast baud rate. It's only 100K baud. So what the engineers decided to do is kind of pack things together. So we get 16 of those variable channels into just 22 bytes instead of 32 bytes. So here is a diagram that kind of shows this. Now, I did, in order to keep the bits in the right place, so, you know, we're going across the screen this way. So here's our channel 1 value. This is 11 bits. Here's our channel 2, 3, 4, etc. And we would have 18 of these. I'm only showing a few. What we're going to do is take the first 8 and then figure out its parity and send it out. Now we have 3 bits left from channel 1, so we're going to grab those, and then we're going to take 5 from channel 2 and stick them together, and then figure out parity and send that out. This is, remember, this is from the transmit side. We're going to do the opposite of this for receiving. But you think of it this way. Imagine you have a bunch of 11-inch sticks, but you can only send them in 8-inch packages. So you have an 11-inch stick and you cut it down to 8 inches and you send it. And then you grab the next 11-inch stick and glue it together and cut 8 inches off that and send it, etc. On the other side, we have to put them all back together and cut at the 11-inch mark. And that's what we're going to do software-wise. But does this make sense of what's going on? This is how we're able to package the 11-bit values into those 22 bytes. And it works out perfectly. If you multiply 11 times 16, it's 176. If you divide that by 8, it's 22. So that's where we're using those 22 data bytes. So this is what happens on the transmit side to get the first 16 channel values that can be variable, anywhere from 0 to 7 FF into those 22 bytes. On the other side, we have to put them back together. So here's, you know, we've received in that packet of bytes. Here's the way the algorithm works on the receive side. We're going to have a workspace and stick a byte into it. Now, we don't have 11 bits yet, which we need for a channel. So we're going to stick the next channel, the next data byte onto the end of that. The way that we're going to do it in code is we're going to keep track of how many bits we have in our workspace, And we're going to grab the next byte, shift it left by that many bits, and OR them together. So that's what sticks it on the end. All right. And now that we have 11 or more bits, we can take these 11 bits and save them somewhere, and then shift this whole thing right by 11 bits. And now we're to here. And the process starts over and over again. So you'll notice it wobbles a little bit because of the difference between 8 and 11 bits. But this is very easy to code in a loop. It takes literally 6 or 7 lines of code to do this. It looks scarier here than it does in the code, frankly, but I want you to see what's happening. Again, we've got these 11-bit values. We're going to send them off in 8-bit chunks. On the other side, we're going to reassemble them, and then we have our value. So what we're primarily interested in today is we're getting out of the SBUS, from the receiver rather, we're getting this packet of 25 bytes. We're going to take byte 1 through 22 and run it through this algorithm to create 16 variable channel values. Okay. Here's what that looks like in a simple form. So this, we'll go over to the actual code, but I've had to do it in slides first so we can turn off the slides and just focus on code after we've done this. So this method called decode SBUS, we're going to pass it a pointer to an array of 25 bytes. It's a packet that we just got in from the receiver. And then we're also going to pass it a pointer to our array of channel values. Now that's going to be an array of 18 words. And then we have some workspace here. So here's a little check. I didn't check the end byte in this case, but you know, if the header is incorrect, then we don't want it to do anything else. What I found too is, I thought about this as playing with it. If there's an error anywhere, I throw away the whole packet, because you'll see there's so much commingling of the channel values within the bytes to determine an error here doesn't affect there. I think is just not worth the trouble, especially since we're going to get a new packet in 7.5 milliseconds. So we just chuck it away. I haven't run into any problems. Everything works really cleanly. So here we're assuming the packet is good. We're going to use this for the new people to spin long fill. We'll take an address and a value and a number of times to do it. So it's going to put 0 into here, here, and here. That's what this is doing. So we start at this variable. Remember, in spin, we do not initialize the local variables. So I'm doing this here, and because I want these all to be 0, that's just the easiest way to do it. I think the fastest. All right, and here's the loop that actually does, remember this scary looking diagram? It all happens right here. You can see it's actually quite easy and elegant. You know, like I was saying earlier, even if you're not a spin coder, if you're a C programmer like Roy, or, you know, I know there's some folks that are using Eric's compiler that are using his basic, you know, this algorithm, I think would be very easy to implement in any language. It's particularly elegant, I think, in spin. So we'll see that. Remember, with the first 22 bytes, we're going to get 16 channels. So that's going to be channels 0 through 15. So this outer loop will process 16 channels. This inner loop is going to fill the workspace until we have at least 11 bits. So this is while the bit count is less than 11. Here's my workspace. I'm going to grab another byte. This advances my pointer, and I'm going to shift it left by the bit count. So that puts it out on the end of what I currently have. And then I OR it together. So there's about 3 things happening there. And then I bump my bit count by 8. So as soon as the bit count of the workspace is 11 or more, then I'm going to save the lower 11 bits. We do have to do this masking because remember, we've got the upper bits belong to the next channel. So this is important. Do not neglect that. And we save it out to the channel. This right shift by 11 bits dumps off the value we just saved, and then we decrement the bit count by 11. So, you know, 1, 2, 3, 4, 5. There's really 5 working lines of code and 2 loop control variables handles that. Now, if you go look up what other people are doing to do this, it's a little on the scary side. People are having these long lists of grab a byte, mask it, shift it, grab another byte, mask it, shift them, or them together, and it becomes very, very convoluted. I will not take full credit for this. This is my variation of it, but oh, doggone it. Ken, who did the control code for the original quadcopter? The Canadian guy.
Jason Dory.
Jason Dory, thank you. He had a version that did a looping thing like this. He did it differently than me, but when I saw what he was doing in a loop, it made sense. This is my variation of that. So I do want to give credit where it's due. I was inspired by Jason's work, and you can see how really simple this is. It's very clean and very easy. Now, the last 2 bytes of the SBUS frame are actually sent as bits in the flags byte. So here we're going to read the flags byte, and then we use a very simple ternary operator to convert a 1 to 7FF, or 0 stays 0, and then we save that out to the channel. So that's the full decoding in spin once we've received the 25 byte packet. It is really that simple. Okay. Now, because we're talking about all the processes, because this is our main focus. We want to be able to do this. And I'm showing here in spin, we're going to talk about it in assembly too, when we get over to the code section. But this, if you didn't want to do assembly, you can do this. It's plenty fast enough. I think I measured, and I have it in the code, it takes less than 1 byte period to do the full decoding of the packet. It's like 107 or 108 microseconds at using interpreted spin 2 at 200 megahertz, which is what I run. If you're running it through Eric's compiler, you're going to get a different result, a faster one. All right, here is the other way. This is the transmit side when we want to do that. It works similarly. We start, though, our outer loop is actually that's going to be the 22-bit bytes rather of our packet. So we're going to build our packet by putting a channel value into the workspace. And we add the bit count, which is 11 there. You notice that we don't have to do this part in a loop to check for the number of bytes, because we have 11-bit sources and our output is going to be 8 bits. So if we add an 11-bit channel, we're always going to exceed 8 bits. Now we do down here check to make sure that we're greater than or equal, because there can come a time in the stack up where you might get to the point where you have 2 bytes in there. But this is doing the same kind of thing where we're taking the low byte out of the workspace, putting it into our SBUS packet, getting rid of it, decrementing the bits, and doing it over. So this is the major packing. The other side of that is this is just handling the flags. And in this case, we just look for the 50% value and set the bits accordingly. Remember, this is channel 17 from the receiver standpoint. This is array index 16, but that's bit 0 and bit 1. And then we write that to the flags byte, and our final footer byte of the packet is 0. So it's actually easy as well. And in fact, my transmitter object for SBUS is only spin. I didn't resort to any assembly in the transmitter object. And it works really, really well. Any questions before we jump into the actual code? Okay then. Hopefully everybody got the code downloaded. I posted it last night, so there was more time. And then I posted a bonus this morning. Program 7 was posted separately. Program 1 doesn't connect to anything. We're just running this inside the Propeller. This just lets us experiment with the encoding and decoding, or decoding and encoding. So what I have here are packets. Here is a channel packet as if we were from the control side, and here would be the output generated by that, or vice versa. Here could be a packet we received, and this is how it would decode. This started as a raw capture, and then I went in and cleaned up the values. Initially, we're going to look at the decode, the receive side. So what we're going to do in the decode demo, we're going to pass, remember that decode method that we just looked at, it wants a pointer to the input, which is the SBUS bytes, the 25 bytes, and then a pointer to the output array. So in this case, I'm going to use this as my input, and I'm going to use this as my output. And you'll notice I left some commented code. One of the things that I do, because I wanted to be able to tell you how fast things operate. So here's how I did that. We've covered this before, but with the get count, we can determine the number of ticks a process takes and then convert it to microseconds. So if you uncomment all those things, you can see what the timing is. And that actually even includes, I didn't even think about that, that includes the call and return. That's not just inside the process, but you can see at 106 microseconds, that's less than 1 byte period. So we have about 4 milliseconds of working time between frames. So it's not a problem. We've got plenty of time to decode and then do the work with. So this is the code we looked at a minute ago. Although you can see I did add better checking the header, checking the footer. I have to increment the pointer because we're starting there. But this is that same bit of code, and there's comments there, so you can just verify everything. And if we run this really quickly, we'll see the output. And if we compare that to here, it should match this. These are matching. And then you can see, remember, here's that 25 byte packet. This byte is the flags byte. So if I set that to 1, okay, we have to make this a two-way conversation. If I set this byte to 1, what change am I going to see in the output? And now I need Ken to play the Jeopardy theme song music.
Da, 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 da.
Yeah, exactly. Anyone? What's going to happen? Remember, that's the flags byte, and I'm setting bit 0. What difference should I see in the output when I run this again?
Free parallax baseball cap.
Oh,
I believe you'll see a change in channel 17.
yes, sir. Send that man a cap. And here, when we run this,
Send me your shipping address, Jim.
Okay.
and there we are. We see that we've set that on, and we can check all the values. So 2 should also do a change to channel 18. There it is. And 3 will give us both of those flags bytes. Okay, so we can see that. So for those that are new and getting into hardware and doing it, this is how I developed the code. I had my receiver. Since I have a little bit of experience, I did a raw capture, and then I cleaned it up and started doing things mechanically. I also did, to be honest with you, remember I was telling you about that big crazy grab a byte, mask it, shift it, or it was something else that you see. If you look at the Arduino libraries for SBUS, they use this process. I converted that to spin just so that I had something to compare with. But you'll see that, the decoding algorithm that we have that runs those 2 little loops is really, really clean and elegant and runs plenty fast for what we're doing, even in interpreted spin. So I compared it. So when you're starting with a protocol, fake it, if you will. Get values or make them up, and so you know the outcome. I knew going in that this was the SBUS frame that resulted in these values. Since I knew that as fact, then I could go and I could tune my code, my decode code and my encode code to match that. Now, this is spin and it works plenty fast, but my thought process was on the receive side, I wanted everything to happen as quickly as possible. Now, this is ultimately going to be running in its own cog, but even then, I want everything to be as quick as it possibly can be. So I did a test and I converted this code to assembly. Now in Spin 2, we can do that in line. We don't have to resort to launching a cog. And I won't go through this unless somebody wants me to. I do want to say though that I got a lot of nice tips from Chip and Tony B and Evan H on the forums. Tony and Evan had some really neat tricks that they showed me. Now I'm of the opinion, because I do these kinds of things, you know, I'm giving presentations. So my code tends to lead to the easier side versus I'm squeezing every last bit of performance out of it. Now, if we go up here to the where we're calling, and so this is decode SBUS. This is just a PASM in front of it. If we do it, if we put PASM here and rerun. Oops, what didn't I do here? So you can see if I do this in PASM, it takes 8 microseconds to convert the 18 channels versus about 108 roughly. So it's significantly faster. Now, that's 1/10 of a millisecond, but in the control side, if we're doing crazy things, I want that speed. So this is why I worked to develop this. We can do it. We can go the same way with the decode. I won't bore you by running those programs, but you can see here is that code, and there is the assembly version of it. Okay, so this was step 2. Literally, it works out really well the way to do these presentations, but this is how I developed the code. Once we had this part working, then the rest becomes pretty straightforward because it's traditional things. Now, the next stage, once we have our algorithms for encoding the SBUS, for decoding an SBUS stream or encoding channel values into a stream, we know all that works. Now we just have to deal with the serial, and this is where we'll want to spend a little bit of time because it's inverted and it has a parity bit, something we don't normally do. So let's look at that.
I got a question, John.
Yes, sir.
Isn't this transmit one way from the, why would you want to encode? You can't send anything back to the receiver. To the
No, but as I said, my end goal is I have 2 of my best friends work in show business. One of them needs to receive SBUS, the other one needs to transmit.
Gotcha.
So I was just, and once you understood the internal mechanisms, it was nice and easy to create both sides. So yeah, sorry, I'm doing 2 things at once here.
Okay.
It turns out to be easy in the end. Again, once I understood, in fact, I was talking to my friend John Huffman, I said, hey, let me try this analogy on you. You have a bunch of 11-inch Lincoln logs, but you got to send them in 8-inch packages. Here's what you do. And he was laughing so hard I had to stop. But that to me, I'm a very visual person, which is why I do those diagrams. I actually wanted to see. I have everywhere next to my desk, on my desk, I have notepads. I'm always drawing little diagrams. I tend to think in pictures when I'm doing code. And so those diagrams that I did, hopefully they make sense. You know, when you look at the code, it's really, really simple. You know, and it matches what the algorithm, you know, suggests it needs to do. Okay, next step is receiving serial. This is going to be serial input. We're going to focus on the receive side now. Remember, with the P2, we have a smart pin mode that is asynchronous serial receive. And in the Spin 2 documentation, there's a constant name for it. It's P async RX. All right. Again, if you go look if you do any research on SBUS receiving, you'll see a lot of Arduino projects. What you'll see with every one of them is an external transistor, because SBUS is inverted, but the UARTs in the Arduino family of controllers are true mode. So you have to add an external inverter. The cool thing about the Propeller 2 is that we can do that with code. So this constant, this is a pin configuration bit that says take whatever coming in the physical pin and invert it before sending it forward anywhere else. This is really fantastic. Makes it very, very easy. Now, when configuring a receive UART on a smart pin, or configuring a smart pin to be a receive UART, the X register has two values in it. There's an upper 16 bits and a lower 16 bits. The upper 16 bits is the baud rate. So remember, our baud rate is 100K baud, and the baud rate is specified in system bits, system ticks rather. So we're going to take our system frequency and divide it by 100,000. That's the number of bits in our, the number of ticks rather in our bit period. And then we're going to shift that left by 16 to put that in the upper 16 bits. The lower 16 bits is our bit count minus 1. So you'll see if you look at any of Chip's code, this is how he tends to do it. This is to say, hey, we're putting 9 bits there. So we do it. The value has to be 8, but we want, this is just a reminder. It's 9 bits. And over here in the comments, you can see it's 8 bits plus a parity. So that's, we want to be able to receive that. All right. So this method, and again, this is experimental code just to get going. This will receive a packet. Now, if you visualize what's going on, you get 25 bytes, and then you have about a 4 millisecond quiet period on the line. Then you get another 25 bytes. What we want to do in order to simplify our life, or at least in my opinion, this simplifies it, is look for that quiet space between the SBUS frames. So that's what this does. Now this is in spin, so this is not timed really well. In fact, I just noticed this yesterday when I was last night when I was doing a review, I thought, oh, doggone it, I don't have any actual timing connected in here. What I want to do, what my intention was, and the reason this says 250, is that I wanted to make sure I had at least 250 microseconds of quiet time on the serial line before I started receiving serial. And it turns out I actually, when I noticed that there's no time, you notice there's no get count or wait count used in this, I took this chunk of code and stuck it into a test program. It turns out this takes about 350 microseconds, so it works. When we're doing it in assembly, we can be a little bit more specific. Just remember the goal. The goal is to wait for that quiet period between the frames. Now, we don't want it to be obnoxiously long because we might enter right before another frame shows up. Now, here's a caveat though. We cannot look at a pin for being high or low if it's configured as a smart pin. Okay, remember, or if you don't know, when you're using a smart pin, the direction bit actually enables or resets the smart pin configuration. In order to get the pin back to a generic tri-state mode, the easiest thing, if you're doing it in spin, is just do a pin clear. That will reset everything. So, so we're doing that here. This code, what it does is it just looking at the pin and waiting for it to be quiet for 250 cycles. In my assembly code, you'll see it's a little more precise, but the point is we're waiting for the quiet time. Once we found that quiet space, we're going to reconfigure the pin as a smart pin so that we can receive the serial. I know this seems convoluted, but I know of no other way to do this. What we don't want to do is enter right in the middle of a stream and get bollocksed up. So this, the 250 microseconds is 25 bits. So that's 2 bytes plus a bit. So we know that we've covered that. And in the assembly version, you'll see that we're actually doing, the loop is running in a 1 microsecond interval. Now remember, at 100 kbaud, a bit period is 10 microseconds. So we're sampling the line 10 times per bit. So we've got plenty of coverage. We're not going to miss a stray bit. We know that when we hit 250 quiet microseconds, the line is at the idle state. All right. So this is the pin start to configure to be the receiver using inverted mode and 9 bits. We don't care about stop bits in the receive side of things. We will later, you'll see that. So with pin start, we're going to specify a pin. This is the smart pin mode. So that's this configuration mode. The X register, that's this parameter of pin start. That's going to get our baud and bits information. And the Y register is not used. So this is reconnecting that pin as a UART. Here, we're going to just wait for 24 bits. Now, the way that the smart pin receive works is that pin read, which, you know, in the past, that just shows us the level. Well, when it's a smart pin, that tells us if information is available or not. So in this case, we're going to wait until we get a high back from the pin, which tells us, yes, I have data. This will now, with read pin, we're going to grab the byte we just received. Remember, it's 9 bits, and we're going to shift it right by 23 to realign the LSB. So now everything is correctly aligned. So here's how easy it is to deal with the parity. There is a built-in function in spin 2 called ones that will count up the number of ones that are in a value you pass. What I'm doing here is this is counting the number of ones, and then I'm masking off. So I'm just looking at bit 0. If bit 0 is high, then we have an odd number of ones, okay? If that's the case, we're gonna return false from this method saying, hey, we had a bad packet. Most time, in fact, I don't think I've ever seen a bad packet save once. It's going to be true. And so what we can do then is we can mask off that parity bit with this and then save the value into our buffer. Notice here too, I kind of blew right past this. I have a local buffer that I'm using. And one of the things that is different for those of you that are new to Spin 2 that might have some spin experience on the P1, in the P2, we can have bytes and words as locals. You just have to, I guess what we call it, cast them on the line. So I'm using a local buffer because I don't want to write to my working buffer unless I know everything is hunky-dory. So here's a local 25 byte buffer. We're writing to that. Once we've received that, we're going to check the header and footers. If they're okay, then we're going to transfer. Remember, we passed to this a pointer to our working SBUS buffer that's out in the outside world. We're going to copy that over and then return true. So this allows us to receive the 25 byte frame from the receiver. So there's a lot of stuff going on in here, but makes it nice and easy. Even in Spin, we can receive, we can enable and disable very quickly the smart pin, so we can look for that quiet space. And that's very useful. One of the protocols that I haven't worked on yet with the P2, although I've done a lot of work with it in the P1, is Modbus. And there's timing things like this that are important there as well. So this is the first time that I actually did the kind of the work to turn a smart pin on and off. Before I didn't want to do that. And it does turn out, if you're doing this in assembly, as you'll see in the assembly version of this, you don't have to do all the work that happens in pin clear. If you look at pin clear in the interpreter, it's clearing the the smart pin mode, the X and the Y registers. It clears everything. In assembly, we only have to clear the smart pin mode. The X we can leave alone, and the Y we're not using anyway. As long as we have 0 in the smart pin mode register of the pin, it will act like a normal tri-state pin, which we need for monitoring that quiet time. Okay, so what this does, now after all of that, this simply lets us look at frames. So if we run this, I have my receiver hooked up. Now, for those of you that are worried, if you look, the output from the SBUS receiver is a little higher than 3.3 volts, but I haven't had any problems. I've connected it directly. If you're nervous about it being a little above 3.3 volts, which again, I think the P2 would tolerate with no problems. What I've done for today on my JonnyMac, I'm using those 4 servo headers that are in the middle of the board. And then I'm taking a wire from that 4-pin female header over to my input pin. What that's doing is it's running the output from the SBUS receiver through a 1K resistor. So we have a little bit of current protection there. I don't think it's necessary. I had it hooked up before. I even hooked it up to an eval board. The one thing I did notice, so I stopped doing that, is there's an overcurrent LED on the eval board that kept lighting up. So I thought, okay, maybe the receiver is drawing more current from the USB than we should. So I switched over to the JonnyMac because we've got a big beefy power supply on that. Again, not a problem to hook it up directly. So I'm going to turn on the receiver, and my transmitter, my receiver light stopped blinking, so I know everything's hooked up. And if we run this program, we're just going to see raw packets. Let me move this out of the way. It is a little wider too. So here are our packets. I'm going to pause this for a second so you can see 0F, that's our start byte. 00, that's our ending byte. These bytes to here, those are the packet, those are the channel value, those 16 channel values. And then here is our flags byte. So we resume this. So once this gets, let me clear this. And now I'm not running this very fast, but as I move around, it may be a little tricky to see through the stream with the compression. But if you look at the kind of the display, you should see a bunch of numbers changing as I'm just wiggling around the sticks. And here I'll flip. I just flipped a bunch of the switches and I'll turn the knobs. So you should see the values changing. Now, remember in the flags byte, there were 2 other bits. We had a lost frame bit and we had a fail-safe bit. Remember this column right here, the second to last, is the flag. So watch when I turn off the transmitter. See, it went to 4 and then to C, and I'll turn it back on. And what I'm going to do, is I will, let me pause this. I want to scroll back up because this tells us something useful. Remember, bit 2 is the loss of frame. So here's where that happened. So bit 2 is set. And I'm running this loop every 100 milliseconds. So you can see if we lose contact with the radio for half a second, then it's going to go to fail-safe mode because you can see it's set bit 4 as well. So here is the loss of frame flag set. Here is the fail-safe, excuse me, flag set. Because I didn't know. I thought, well, I wonder what it tolerates. Turns out it's half a second. Okay, so this is the packet. So again, even in spin, we're able to receive the packets from the radio without any problems. Questions? Yeah, it's pretty easy stuff, right? Bueller?
I never imagined it to be this simple.
You know, what I think too, and I hope that you mean that. I think you do. when I was looking in the outside world and people were saying, well, Futaba uses standard serial, everything is inverted from that, I was very confused because I was looking at an oscilloscope and I was saying, no, that's inverted, that's not. So if we go from the framework of the electronics world, the Futaba SBUS protocol uses inverted serial. The IBUS protocol, which I think I mentioned earlier, the IBUS, which comes out of this by default, uses true mode serial. It should be actually quite easy to do an object for because it uses 2 bytes per channel. It doesn't do any byte packing. And it uses a standard baud rate of 115.2. So I'll do that in the next couple of weeks so that we have both, because as Ken has pointed out, and I pointed out, for $60 for a transmitter and receiver, that's a pretty inexpensive control device. And it could be, we're gonna do Ken's boat. I fully expect that Kevin is going to have a rolling robot in the next couple of days controlled by this thing. My friend Rick does movie stuff. I think a long time ago, I showed some pictures from a project that he did right before DEF CON 22, where it was a Sony commercial, and they had snowboarders, going down hills that were all lit up. They had 2,000 neopixels on these snowboarder costumes. It's crazy because the snowboarders had to wear 80-pound backpacks for all the batteries. The way that they controlled the colors on the snowboarders was through an RC transmitter. Now, back then we didn't have SBUS. I wrote an object for Rick that would take the outputs from the receiver, the parallel outputs, measure them, and then provide data to his program. This is so much easier, and it only takes 1 pin. Okay.
One question or comment, if possible. As far as I know, usually the transmitter have also an SBUS plug for training reasons. Yeah. So you can connect 2 of them together, and basically couldn't we connect your SBUS transmit there with a P2?
Well, I haven't explored the trainer port on this one yet, Michael. I have on other devices, and normally what happens that there's a DIN plug back here that is a trainer port. And what I've seen in the past, because I've used this for animatronics control, is the output from here looks like pulses, like servo pulses, but they're individualized in a frame. So you have to measure them. Again, I have not dealt with this one yet, but I will, because $60, again, really hard to beat. So I'm gonna figure out all the cool stuff. I started with SBUS because, as I pointed out several times, I have 2 really close friends that need SBUS. One needs input, one needs output, so that's where he started. And SBUS is in the RC world is the standard. There are others now. There's iBus out of this, but SBUS comes from multiple manufacturers, so that's where we started. All right, so we know the algorithm for decoding an SBUS packet. We just showed how to receive it, so we can now put it all together. I believe this is what this one does. Well, let's just run it and see. The transmitters, if you're new to the transmitter, this guy wants the throttle down and all the switches up if you're in 10-channel mode before it'll do anything. So watch, if I turn it off, I have the throttle in the up position. If I turn it on,
it squawks
until I set it to off. So it's a safety thing, I'm sure. Because this could be on an airplane with a propeller.
Hey, John?
Yeah.
I remember back when I was a kid, when I was playing with this stuff, that there was actually different frequencies, and they had air radios and they had land radios. Is that still the case, or is now everything just digital and doesn't matter anymore? Yeah, no, it's these 2.4 gigahertz transmitters and receivers are all in the same frequency range, but they're bound together. So when you buy this as a packet,
the transmitter and the receiver are bound. So fair warning, because I found this out the other day when I was practicing, if you do a factory reset on your transmitter, it will unbind from your receiver. So it's actually quite easy to rebind it. In the packet, you'll get a little plug that you're going to plug into the end channel. It says bind on there. And there's a button right here on the bottom of the thing that says bind. So you turn off the transmitter, you press and hold the bind button, and then turn on the power. When you have the binding plug inside the transmitter, or sorry, the receiver rather, it will, the LED on the receiver will flash really fast. Once you turn on the power with the bind button held, it will go solid and the binding is reestablished. That allows you to change which receiver you want to talk to. I assume, I don't know, maybe Ken knows because he has more RC experience than me. Maybe you can bind to multiple receivers. I don't know if that is possible or even wise, but that's how you do the binding. Again, so there's no, I had an old transmitter from something where you could actually change the crystal from the outside. That's not the case with these digital transmitters.
Yeah, that's the way the old Futawas were. They had a crystal with that little piece of cloth, and you could pull them out and change them.
Yeah, yeah. I think these are probably a little cleaner because remember, it is data. When we do that configuration, it has to pass that over to the receiver. The receiver, remember, by default wants to do iBus as the output, but we're telling it SBUS. So it's not just a simple packet that is going, and this receiver in iBus mode anyway, it's two-way all the time. When you first turn on the transmitter, if you look, it will tell you the battery, the voltage going into the receiver. So there is always a two-way, there's always two-way messaging between the transmitter and the receiver. Now, I am, like I said, in the next phase of this remote control stuff, especially since Ken wants to put this onto his boat, is to figure out how to do the iBus telemetry stuff. So I'm hoping that we can, in fact, get data across right on the screen here. Sorry, my green screen's killing me. But if not, another thing, since we have the code for it, is we'll just transmit the data we want via XB and then display that on another monitor in any fashion we choose. Okay, so this program 3 now takes the receive and the decoding and sticks them together so that we can see values. So here I'm running this, and as you see, as I'm moving around the sticks, the flashing thing, I'm receiving the packet. So when we get to this point, we know that we can use SBUS. This number up here is just the number of packets, or the number, it's just a counter to see that everything is alive. So we know it all works. Now, in this, remember, we only have a 10-channel receiver, so you'll notice that the transmitter defaults channels 11 through 16 to the midpoint, and 17 and 18 to off, because those don't exist on this transmitter physically. We can go, you see channel 10 is this switch out on the end, and that's as far as we can get. But now we have kind of working code. It's not particularly, oh wait, forgive me. Yeah. So this is still doing everything in spin, technically. You see that the whole works is in spin. What we're going to do, though, is package everything in a nice object. So that's what program 4 does. So program 4 will look similar, but this attaches to an object called JM SBUS RX. So if we look at that, and I'll just look at it briefly, it allows us to have background reception and decoding. And so we don't have to think about it. It's happening in its own cog, and we're not worried about timing. We can grab values from it at any time. So in this, we'll talk about this a little bit. This shows some of the really neat stuff in Spin 2. So the start method is quite easy. We're going to send it the pin we want to use. and a pointer to an array of default values. The reason I did that, and it turns out maybe it doesn't really hurt or help anything, is I thought, well, what if I don't have any values coming in? The receiver is not turned on or something goes wrong. I wanted to have a set of default values. So you can see in the application code, I have an array called defaults, and I have everything set up to the center values. These are the switches, or on this transmitter, this is the right stick, this is the left stick, this channel being the throttle. These are the two knobs on the top, and then we have the next four are the switches. These are the unused channels, and here are the last two digital channels. So that's just the default value. So we're going to pass a pointer to that. This is 100% assembly, so I'll go through it very quickly, but I want to show you something or show you how that we merged all those bits together. We do need to pass some information to the background cog. So we're going to pass the pin, the number of ticks in 1 microsecond, because remember we were talking about that timing, and then a pointer to our channel's value. This is going to be the array of decoded channels. So if we pass a valid address, which is anything greater than 0, then we will put the default values into our channels. So if you don't care about that, just pass 0 in that parameter and it won't do anything. This makes sure the pin is cleaned up. This is a little fancier version of doing the bitrate calculation. This was a trick from Chip, so I use it. Again, with receiving, we want 9 bits. And I initially do a pin start here. Now here's a thing to understand with the smart pins in the P2. If a cog, any cog, configures a smart pin, it's a smart pin, that same smart pin for every other cog. Okay, the smart pin stuff exists within the pin, not within the cog. Okay, so this actually helps us because using pin start is very simple. So this is initially setting my pin. Here's my SBUS configuration. Now I've moved it down into the assembly code because we need it down there later. But you'll see it's those same constants. Here we're doing async receive and inverted. And then X is our baud rate and bits. And now here's where we start a cog. So we're passing the address of this variable. Now, there's an interesting thing in the P2, if you haven't done any assembly with it. Remember in the P1, when we would start a cog, we would pass it an address, and that went into the PAR register. And we often refer to this as the mailbox. Well, most of the time we would want to deal with more than one address in the hub. So in the cog side of things, we would have to copy PAR into another variable and then manually add the offsets and do all that. We don't have to in the P2. Now, it's not called PAR anymore. It's called PTRA, but it's serving the same purpose. The value that we pass in the cog init goes into PTRA, and that has an offset of 0. These values, because PTRA is this address, well, PTRA sub 1 is this address. So we can treat this set of longs as an array called PTRA in the cog. It makes things really, really nice. So here we have, as I said, we have to pass the pin to the cog. We need to tell it how many ticks are in a microsecond. We need to tell it where to write the values. pchans ends up with the address of this array. Frame loss is a flag. Failsafe is also a flag. Frames is the number of frames we've received. And updating is the point where we're converting from the raw frame to our channel values. We probably don't want to be grabbing stuff while that's happening. It only takes 4 microseconds, so there's not a big wait when it's doing the updating. All right, so I'm going to skip through fast. We've started the things going into the code. This nifty bit of code, again, the nice thing about the P2 allows us to read those first 3 longs into the cog, into these variables, into the cog. This is so much easier than it was in the P1. Okay, these are the things that we need for doing things. After that, you'll notice this is going to follow on exactly like the spin code. So the first thing we have to do is restore the pin as a tri-state pin. So, you know, normal IO pin, so that we can look to see that it's not busy. So float low takes it out of the smart pin mode. It disables the smart pin without taking out the smart pin mode. By doing a write pin 0 to that pin, we clear that smart pin mode out. Now it will behave like a standard tri-state pin. The X register is still intact. That's got our bit timing and our bit count, and it doesn't hurt anything to do that, but we do have to do this. I wasn't at first, and I was getting some unexpected values, and I checked in with Chip, and he said, no, you have to do this in order to have the pin behave as a normal standardized tri-state pin. This little code here is at 250 microsecond wait. Now I'm doing a countdown instead of a count up because it's just a little easier. So at the top, we're going to set a temporary variable to 250. We're going to wait 1 microsecond, and then we're going to look at the pin. This is so much easier in the P2 than it is in the P1. So test P looks at this value, and then I'm going to stick it into the C flag. Remember, we want the C flag to be, we want the line rather to be low for 250 microseconds. So this is saying, hey, if C is high, then jump back to the top, which resets our timer. So what we're going to do is, while we're seeing stuff going online, we're just going to be constantly resetting that timer, kind of like a one shot. We keep resetting it. Once the line is quiet, because if this results in 0, we will not run this line. And then we do a decrement of that variable. And if it's not 0, then we jump back and wait for another microsecond. So this is a very tidy bit of code that waits for a quarter of a millisecond. Once we've done that, we know that the line is quiet. This write pin puts back our smart pin mode into the pin, and then we have to activate it by driving the pin, the dir register, the dir bit rather, a high or low. We just have to drive it. That's what does that. And now what we're going to do is receive 25 bytes. And remember, in the spin version, I used a local array called buffer of 25 bytes. It was local to the method. Here, we're going to have an array in the cog. The P2 makes this much, much easier to do than the P1 as far as, arrays inside assembly. So this is the loop that receives the 25 bytes. The first thing we're going to do is do a test pin on RxD. Remember, that will tell us if there's a byte waiting in the 1 byte buffer of the smart pin. And that is important to remember. When we're using smart pins for serial, we only have a 1 byte buffer. So we don't want to lollygag as far as looking at something being available or not. And in this case, we're doing it in a very tight loop, so it's not a problem. But this will wait for a byte to receive. This will grab the value. We're going to shift it right by 23. We've all seen this. This is an exact duplication of the spin code. We're going to count the number of ones in the byte that's in T1. This will be the number of ones. We really don't even care about that because within the ones assembly version, if you specify WC, that will be set to 1 if it is an odd parity. So if that's the case, if we have a bad parity bit, we'll jump out to this thing called bad packet. Usually not the case. And here's what I find just magical. This instruction, Alt-SB, will alter the set byte instruction that follows. And what it does is it alters the destination. You can think of set byte, or this is how I think about it. So if I'm wrong, Chip, please correct me. But I think of set byte kind of like the internal cog version of write byte. Now, write byte writes from the cog to the hub. Set byte writes from the cog inside the cog. And the destination is set by this instruction. So we're going to start here. We have an array that's defined down below called SBUS raw. That's the address of it. Now remember, in assembly, hash symbol is for the base address, yes?
That's right.
And then we're going to take that base address and we're going to increment it by whatever that value is. So iCog is my index for the cog array. And now we're going to write to the address that this set up for us, the byte that we just had. Since this is only writing 8 bits, we don't have to fool around with the parity bit. It'll get truncated in the process. Here's another nifty instruction called encoding. What it does is if this value is less than this value, it will increment this value. If they're equal, this value will be set to 0. And the C flag will be set if we allow that. That's what we're doing here. So here's what we want to do. We want to count from 0 to 23. To 24. That's because that's our 25 byte packet. Once we process byte 24, then what will happen is this will get changed to 0, that will get set, and this will fail, so we'll fall through. Otherwise, we just loop around in there. But you see,
Hey,
this,
Jonah,
yes?
did you know that where you have the pound SBUS raw,
Mm-hmm.
you have to use, to get any more than 9 bits, you would have to use a register with the value holding SBUS raw, but bits 9 through 17 are sign extended and added to iCog in that instruction. So what you could do is put SBUS raw into a register and then OR 200 hex into it. And that Alt SB will then also increment the iCog variable.
Okay.
Um,
I'm going to keep it easy for the time being, because even I can understand this. Now, I wrote it, but I want it. This works nicely, and to me, it's very easy to understand too.
yeah, it is.
So that, again, as I said earlier, I'll never write code as tightly as you do, or Evan, or Tony B. I want it to work and work efficiently, but be easy for everybody to understand. And I like this. This makes, once I saw how this worked, I was thrilled, because I thought, oh, I can do all kinds of fun stuff with this. So much easier than on the P1, because I did write a P1 version of this later for Rick, because he needs P1 stuff right now for what he's doing on Star Wars. And it was not as easy as this. So again, I'm going to try to speed up a little bit so we don't spend too much time on this hardcore stuff. But this section right here receives our 25 byte packet. And so long as we don't have any problems with parity, it will fall through. If we have a parity error anywhere in there, we jump to this thing called bad packet, which we'll look in a minute. This will check to make sure those first and last bytes are what they should be. Now, I'm sure Chip will jump in and say, oh, there's a tighter way to do this. This is the obvious way. What we're going to do is we're going to grab byte 24. So I'm putting 24 into iCog, setting up my thing, and I'm using get byte in this time. Notice this changed from Alt SB to Alt GB, because it's affecting the destination, or it's affecting the source for this get byte. So this will contain my footer value, and I'm going to stick, so that's in T1. Now we're going to grab with this, or we're going to set up to grab the header. And this is a nifty thing. Instead of just grabbing the byte, we grab it and we roll it into the value. So if this is my first byte, and I should do it this way so that it looks correct on the screen. So here's what I've got. This is currently my footer byte. And then I do the roll byte to the next byte, it's going to push it in and become the low byte. This is now the low byte. So what that allows me to do is a single comparison. Remember, I should have a footer of 0 and a header of 0F. If it's not that, then we have a bad packet. Again, This was the easy, obvious way. There may be better ways, but this, I wanted to keep it clean and easy. So we've done parity checks while receiving the packet, and now we have the correct header and footer. There's really nothing else we can do to validate the packet. And now we can convert the packet into the 11-bit values. So here's where that pointer A with indexes comes in handy. If we look, index number 6 in that array is the updating flag. So that will tell the foreground, hey, we're busy, updating things. So we set that to on. I won't go through all of these things, but this is the assembly version of the decode. The one thing I will say is that we are passing, remember, we have this thing called phub. There is pointer A, which we're using as index, but there's also a pointer B register that has this really handy little feature. I think this exists in pointer A too, but I'm using it here. Normally, when we write to the hub, we have to then modify our hub address. We don't have to, or we can do that automatically by copying our base hub address into pointer B. And you'll notice when we do a write down here, if we write the value to pointer B and do a ++, this is a smart instruction in that it will increment pointer B by the value that is necessary for the write command. So in this case, we're going to add 2 to pointer B since we're writing bytes. Remember, a word is 2 bytes. So this process will convert the 25-byte stream that we have sitting in the cog to the hub variable. Again, I measured it. It takes about 4 microseconds. Here's where we do the flags stuff. Now, this was an interesting thing. This is a little less obvious than I'd like, but it's enough. It shows the power of the P2. This was, I think, from Evan or Tony B. I don't remember. One of those two guys showed me this trick where we can grab the flags byte, test the bit, and that goes into bit C. And then using this bit C into the workspace, this is a bit field of 11 bits. So whatever is in C will get stuck into 11 bits of the lower 11 bits of the work byte. And
Hey, John.
Yep.
We actually have an operator that will do that for you. You could just say #0 and then add bits 10. And that would mean starting at bit 0, add 10 more bits. So set all those bits to the C flag.
Yeah, so change that plus to add bits 10, or change this to add bits 10. Is that what you're saying?
Yeah, it would. Yeah, that's it'll do that math for you. And make it a little bit easier. Yes.
Oh yeah, no, I will change that then later. I didn't know that. Again, this was code that Tony or Evan suggested that's creating the bit field, but I didn't know. So in a way, we're using this spin. I guess it's all spin technically. Add bits that we normally think about in high level spin, but we can use that in the assembly because it happens up a front. It's part of the assembly process, not a live thing. Since this is a constant, that's what it works, right? Okay, I will change this and then republish this later. Cool, that makes it even easier to understand. Anyway, the point of all this is to convert bits to their values and write them out. Now, we do have 2 other bits from the flags byte. We have the frame lost bit. That's bit 2. So we're testing bit 2 of that, and we will. This is a trick I think from Evan. The idea is that I want if that bit is 0, I want 0. If that bit is 1, then I want true, which is -1. So the idea is sub x, if you subtract anything from itself, you get 0, but sub x will add the C flag into this second value. So if that bit was set, the result of this sub x will be -1, which is true. And then we write that to its flag variable. And we're doing that 2 times for the failsafe. The last part of it, if everything is hunky-dory, is we're going to grab this is the frame count from the hub. We're going to increment it and put it back. The reason I do it this way is so that if the user says, hey, if I have a problem and I want to reset the count, they can do that. So the background is just incrementing whatever was out there. And then we turn off the flag. We're done. Remember, if we have a bad packet, then we'll simply turn on the lost frame flag in the hub. So that's what's going on there. Remember that if that happens, we immediately exit. On the next time through, let's say we get a good, everything is working fine, and the frame lost flag is 0, that will clear it right there. So we don't have to have any other special condition. This is a little involved, but you see the output is, nice and tidy, and we get the, oops, what am I doing? Oh, doggone it. Oh, so on this version, so what I did was, since we have this is using the background cog. So you see, it says it's in failsafe because I had the transmitter turned off. Now it should come back on, so it's online. What I'm doing is I'm measuring the number of frames per second just to see what's going on. Oh, this young lady with chip, I thought she was waving at me. Here are the channel values. Now, here are the channel values from that come raw out of the stream. But I thought I'd show you, because you may have a robot project or something you're doing where you're using standard servo values. So there is a method in here called map that is something that I liberated from the Arduino world that will take a value that is in this range and convert it to that range. It's an MX plus B thing. So if we look at this output, so here are the, let me clear this. Here are the 11-bit values from the receiver. You can see it all, does everything. And then these are mapped to standard servo values. So you can see, if you look at the switches from channel 7 through 10, they're all up. If I set this channel 7 down, you notice how it changes to 1807 from the receiver, but I mapped it to kind of a standard servo value. So it's something that may make your life a little easier when adding to a robot. And finally, on the receive, if you're using Propeller tool as I am, then this version, it does the same thing other than the frame count. What am I doing? But this version uses a graphical output using debug. So I'm sorry for the people that are not using PC Propeller tool. This is only available there. But you can see here, and I had created this really for my friend Rick so that he could tune up a robot. Like in his Star Wars robots, he has a receiver, and the idea is that if he was doing a propeller control, he could move a function of the robot, say an arm, or do whatever he's going to do, and see the values on the screen, and then build in limits into his code if he needed to. So that's what this is, and kind of shows off fun stuff that you can do with the graphical output. So I was actually kind of happy with this until Carol Moore did his really cool NASA output. So you can, it does take a little bit of work. I'm not going to lie to you. If you look at the code, the debug code does take a fair bit of work to do fancy screens like that, but it does give us the ability to do it. So that's kind of neat. All right. Finally, and I will go through this really, really quickly, is on the serial out. We've seen the process already, so we can, in fact, this code doesn't actually do anything because I don't have any inputs on the JonnyMac yet. But the idea is that you can process your inputs, and over here that will and then this is just running in a loop. And the first part of that is grab your pots or your switches or your values. You want to wait until the busy flag is cleared. This is from the transmitter because you don't want it to be, now in this case, the busy flag is saying, hey, I'm grabbing your values and converting them. So you don't want to change values while the background is grabbing them. Once that's not busy, then you can move your channel values over to that. And I have in that simple object it exposes the address of the values, so it's really easy. You can set the channels individually as well, but you can also do it in a block move like that. So if we look inside the code, so this is the transmitter object, and this is 100% spin. There's no assembly required in this. Now, a difference, now remember, we're doing output. So we have a different smart pin mode. It's async TX. We still have to invert it. And one of the things, remember, if you have a smart pin that is outputting something, you have to enable that output with this flag. So this looks very similar, it should, to the receive code, except now it's doing transmit, it's doing an output. Here's another caveat though. Remember, we have 8 data bits and we have a parity bit. The smart pin doesn't know about parity bits, so we have to fake it. What we're going to do is say we're transmitting 10 bits. So and the reason for that, sorry, is that we're going to have 8 data bits. We have a parity bit, and you'll remember on the, the specification is 2 stop bits. So we want to create an extra bit period in there. And so we're gonna fake that as well. So once we've set up our smart pin, we don't actually have to worry about deconstructing it. This code is going to get loaded into a spin cog. And so here's our background loop. What it does is it sets the busy flag so we can tell our application, hey, we're grabbing your values and encoding them. That's what happens here. This should look very familiar. We've gone through this a couple of times already. Then we clear the busy flag, and then we're going to transmit those converted values with this. So you'll see this is, again, really, really simple and 100% spin. Here's how we transmit SBUS using smart pins. We're going to loop through the 25 bytes of the bus. We're going to grab one. We're going to count the number of ones in the byte, and then we're going to set bit 8, remember that's our parity bit, to whatever bit 0 is of this. Works out really simply. We're going to fake that extra stop bit by setting bit 9 to 1, and then we write it to the smart pin. This loop will tell us when the smart pin is done transmitting, and we can go grab the next. Super easy. And if we look at it, in fact, what I'll do is I will, I've got a logic analyzer hooked up, so I'm going to go ahead and run the little demo program. Where is it? 6, right? So if I run this, not a lot going on, but if I go to the logic analyzer and so here's a bunch of packets I captured earlier. Let me make sure I've got the right. Oops. Oh, I want that to be on. And that should be fine. If I run this, live demo bites me 2 weeks in a row. Come on, this worked earlier. Why am I not? Oh, I know why, because I didn't put a trigger on here. Come on. Okay. Oh, doggone it. I'm going to ask you to trust me. This kills me when this happens. I left the logic analyzer open because I want to show you, but it does work. We get the proper output from the transmitter. And so now we can receive. If we want to control a robot or Ken's boat or one of Rick's Star Wars characters, we can do that. For my friend John, on a project that we're going to do another version of, is specialized camera control system that uses a gimbal that comes from somebody else that takes SBUS. Now we can do that. The one last thing, since we're coming down to the wire, I had told somebody this will be about a 2-hour session. And I talked to Chip about this earlier. I wanted to show you, remember, this is a spin cog. This is all running in spin. One of the things that comes up frequently in the forums is, and I blew right past this. Here is how we start a spin cog. We're going to use cog spin. We're going to tell it to select an available new cog. We're going to point to the method that is going to be kind of the top level, if you will, of our application, the spin cog. And then we have to give it some stack space. Now the stack space is available RAM that the interpreter that's running this other cog can use for temporary things. This is always a question that comes up in the forums, is how big do I make the stack? I've gotten pretty good at guessing on the P1, but I went back and I had done that. I'd done a process I'm about to show you with this program, so we'll go through and show you. This is what I do for one I don't know, and with the P2, since it behaves differently than the P1, I need to look at it. I have that same SBUS object. You know, I've appended dev to it. This is another version of it. So this would be, in the actual timeline of things, this would have come first. What I'm going to do in here is put this section. I'm going to start with an arbitrary stack size of 128. That's actually quite a lot of RAM for most projects like this. And in order to figure out how much is being used, before I launch the cog, I'm going to fill the stack with some known pattern. I happen to use this one. You probably don't want to use 0 or all ones. You want some recognizable pattern that's not likely to be a data value. So up here, in the start method, I'm going to fill the stack with this value, you know, and that many. I'm using a constant here temporarily. Then I have this method that will get pulled out later, but what it does when it calls it, it will go this really should be, stack size -1 if we're doing things cleanly.
Thank you, John. That was bothering me.
Yeah, I had fixed values and I decided I should make that nicer. So sorry I didn't do that before I uploaded. So everybody fix your code. Anyway, this will go from the top of the stack down until it finds something that isn't that pattern byte. And this will tell us how many longs rather are being used in the process. Now, I'm going to ask Chip to jump in and talk about this a little bit, but you know, where things get used is every time you do a call. Remember, this is our main loop of the background cog, but it has to call this, and it has locals. It doesn't make any external calls, but there may be some things that the interpreter needs that I don't know about. And then this gets called. So there are requirements, you know, that are going to come up in the course of operation. Now, if we run this, what I've done this is the test version for this. What I do is we know that the background cog is running every 10 milliseconds. We've set it up for that earlier. And so every 100 milliseconds, what I do is I just change the values that are going out of the SBUS stream. The idea is I want to make sure everything's getting worked. And after I've done that 10 times, so every second, I look at how many longs have been used in that cog. So this is where it's pulling that in. So if we run this, it's actually really low. So you see after a second, so we had preset the stack to 128 longs, but we only need 36. Now, I would never be so I don't know, callous as to say, all right, I'm going to set it to 36. I have this weird thing with 16. So you'll notice in the final version of the code, I have a stack size of 48 longs, which is going to be covered. That's 12 more than it looks like I'm ever using. So I'm plenty safe. But Chip, is there anything else that you wanted to share or can, help us out with that? Because this is a question that has happened since the days of being able to launch a spin cog.
Right. Because we have, fixed memory allocation, we don't have any kind of dynamic heap and all this. So you want to size your stack to what it needs to be and not much more. But a rule of thumb is, I think it's like for every stack, every call level within the thing that the cog is running in spin, including the first level, allocate 6 longs plus a long for every parameter, return value, and local variable that amounts to a long. And so every time you do another call and you descend deeper, you're adding 6 plus whatever the parameters plus return values plus locals are. So if you had 5 routines that each required 10 longs, then you'd say it's going to be 6 plus 10, that's 16 times 5 would be 80 longs. That would be your rough minimal requirement. But I'd always add something to that. Like when you do a for next loop or we call it a repeat, right? And you're using, either a value, a count, or a variable that you're incrementing or decrementing and checking. That's going to take 1 or 2 or 3 stack locations.
Yeah.
So these things all kind of compound. So I would maybe you're always going to have to kind of estimate unless you make something like what John did here, but just err on the side of be liberal about how many longs you allocate. Don't try to be too conservative because it may not be worth it.
Right. Well, yeah. Certainly, I've crashed a couple of programs, but on the other side of that, I've had people send me code and they say, hey, I'm trying to run a spin cog. We have a look at this. And I've seen people, allocate 256 longs to a stack.
Yeah.
One tiny loop of code. So say, hey, that's a whole kilobyte of code you're killing. So there is a way. This is not something I created. This trick was from Phil Pilgrim. He had shown something like this in the forums ages ago. And you see, it's just a tiny bit of adding code and doing a check and then figuring it out. So again, the development process is iterative. So for the new programmers, be patient with yourself. These things go chunks at a time, and you'll notice I'm very much this way. Anybody that's worked with me knows I like to work in very small increments and make sure everything is working before we move on. Otherwise, things get a mess. And that's been my experience. So that's why I do things in this manner. I just wanted to share this since this may be the first, since we've been doing these presentations, the first object that I've offered up that is a spin cog. I was going to do this in assembly, but it works so nicely. And since it's running in its own cog, I'm not worried about any impact on the foreground time that it just didn't seem worth the effort. I mean, it wouldn't be hard to convert to assembly, but it didn't seem worth the effort since it runs so nicely and it's so easy to do in spin. And being that we can launch another interpreter and run that in its own cog, it just made sense to do. Okay, this was a little more hairy than I expected. I hope everybody hung in and found it interesting and something valuable in there. We're at that time where I've shown you all the code that I've written. It's been a fairly quiet day today, so I hope that is, wow, this is so interesting. I just want to take notes. But if there's something I missed or we want to know or talk about, or otherwise we can just go to our normal open session and talk whatever we want to talk about. But I'm free to answer any questions.
Thanks, John. Are there questions for JonnyMac?
I took a lot of notes, which is one of the reasons that I was quite silent. You said that you also placed this source code somewhere where we can look at it.
Yeah, all of the code that I showed you today is in the P2 forum there's a thread called Spin for Beginners, SBUS. So all the code that I went through is on that thread.
Okay.
Yeah, I try to upload. I'm trying to get even better. I try to upload all the code that I'm going to present the day before a presentation, so that you had time to get it and look at it and try it.
Okay.
But all of this is available.
The link to that thread is in the chat early also.
Oh, okay.
Dennis just relinked it too. I didn't have a question. I was just commenting that it was all very clear and much simpler than I was expecting it to be.
Yeah, very, very, very well done, John. And like I said before, it was a hell of a lot easier than I thought it was going to be.
Well, and I would suggest, if you go now, you're better armed. If you go to the internet and you look at other SBUS stuff, you might say, well, wait a minute. I tried to keep it grounded in electronics. I wasn't, and I can understand the people from the RC industry, they're looking at Futaba as the standard. Futaba didn't create PTL serial communications. They're just implementing it. So we're going from a different point of view, but hopefully it all makes sense. It is easier than I thought too. Once I got into it and started looking at it and playing with it, it turned out quite nice, especially once I understood the algorithms.
John, it'll be interesting to see how Futaba replies to my inquiry for SBUS servos controlled by
really?
the Propeller.
Oh, shit. You say,
Considering
hey,
they don't publish the spec.
Right. Well, it is really funny. They don't publish the spec, but you can go, I'm now just added a couple of libraries to bunches of libraries that are out there. Although in the Arduino world, it's the same library. I'm going to ask if it's okay, just to see it and to have it, if Roy or one of the other C programmers would just convert these programs to C. So we have a native C version. I think that would be nice.
And also, I'd like to throw out a prize for the first person who provides a useful example of this object, controlling whatever it is you desire, which would be a Parallax GPS module for the June presentation. And the only requirement is you have to be 10 years or older to participate.
Kevin's going to get it.
Yeah, he's going to have a robot running.
He'll have a robot in the next hour.
Yes. I was counting on that. I know he's going to, which will be great. He's got robots, and I think he already has one of these radios, so he's ready.
Yeah.
You can't let him win all the time, though.
That's
so
okay.
The next big robot, somebody must have something else to control. We'll see. I'm sure he needs a GPS module, though.
John, I'm sure your friends probably in the movie industry probably have 20 or 30 channel controllers they use.
Yes, yes. But, Rick was very happy when I did this because, well, I don't tell stories out of school, but he's had to use other processors because they didn't have an SBUS receiver for the Propeller. And he does, anytime he can deploy a Propeller in what he's doing, he does it. He's comfortable with it. He's built his own several Propeller boards. He has a P2 now, so he's moving into that. But, I reached out to him last night to see if he was going to be here today. And he said, no, rehearsal. And, he's really, really busy. I mean, this is a blessing, of course, in the crazy age of COVID. But with the success of all the Star Wars TV shows and the company that he works with called Legacy Effects, they're doing a lot of work building costumes and robots and animatronics and set pieces and all kinds of things. So, but now he has P1 and P2 code that he can deploy as he needs. He doesn't have to use anything else.
So you wrote an SBUS receiver in what, 20, 30 lines of code?
Well, it works out really nicely. Yeah, in the P2, it's particularly easy. In the P1, you have to do it in assembly. And it's a little harder. Now, again, I will thank Jason Dorey. He had written a P1 SBUS receiver. It just, his style and mine didn't kind of mesh, but I tried to learn from him. Again, for new programmers, that's always the thing. You might not write code the way I write code, but as I was trying to do today, I was trying to explain the process and understand the algorithm behind it. Again, you saw how simple the code loops turned out to be. I'm certain that the algorithm that I presented versus the grabbing and masking and shifting and ORing, that is used in the other parts of the world. I think that little loop code that I came up with, I think you could deploy that in any language. And you saw it was super easy in spin, and it wasn't really very difficult, even for a kind of a beginner at assembly like me, to deploy it. Now I got some good hints from Evan and from Tony B, and Chip, and even more today. So
at the beginning, you said you changed your firmware. I did a little bit of searching, and it looks like there is a bug in the firmware, but iFly hasn't fixed it. But there's some guy that's got one on GitHub with the problem described, with output from his and output from the other one graphed, and his patched firmware is a huge difference in the wave, in the graphical waves coming out. They're a lot smoother than what it is from iFly. If you Google it, you'll see it.
So can you put a link to what you're looking at? Because since I'm going to do the iBus next.
Yeah, no, I think he said it was the SBUS. Yeah, let me go back to that.
Now, at least on my receiver, I have looked at this. You saw, I showed you my.
Here, I'll put it in the chat right now.
Okay, thank you. I've looked at things on the scope. I've looked at things on the logic analyzer, and I've not seen any problems. And the data comes back as it should. Now, I only have a 10-channel transmitter.
I don't think what you're doing, you're going to pick this up. This is more nitpickety stuff than anything. But if you look at the graphs there where he shows the transmission data with the old firmware versus his firmware, how much smoother it is.
Okay. I'll read this later. Oh, so he's changing something internally.
Yeah, he said that it doesn't affect the actual functionality. Most people won't see it.
Okay.
But it's a software issue, not a hardware issue. And he patched the firmware to make the transmission a little smoother on the transitions.
I was mentioning earlier, I have this funky thing that after a bit, if I take my channel 1, which is the right stick horizontal, that's channel. Mm-hmm. If I pull it out the side and let it go, because I don't have any kind of rate control or anything on there, most of the time it'll snap right to the center value. But sometimes it goes this, and then it creeps into the center as if there's some, I don't know if this is that will affect it or not. It bugged me because none of the other channels do that. And
this could fix it, but he said that they would, he communicated with them and they refused to fix it.
Huh. Oh, well,
But, I mean, if you look at the graphs he shows, he clearly shows that there's definitely some bugs in the software.
Interesting. Well, the other thing too that in the real world is this is kind of a closed loop system where we've got a transmitter in our hand and we're looking to see what's happening. So we're, even without consciously thinking about it, we're making adjustments. So maybe that gets covered. But I'm going to read this and I will, again, there's no harm. I've flashed this once already, so I can do it again and see how that.
This isn't firmware from the company. I guess he somehow got the firmware out of it and hex edited it and fixed it. Because
I understand that, but I have it's easy. I mean, they make their official firmware easy to get, and the device comes with a cable. So again, no harm in giving it a try.
So do you use the trainer cable to upgrade the firmware?
Yes.
Yeah.
Yeah, it has a USB connector on one side and the DIN plug on the other.
Right.
Okay, we're going to switch gears now to keep it going. And Stephen, you ready to talk about Hub 75?
Oh, I guess I can be. Sure.
Thanks again, John. And
thank you, guys.
Still questions for John, just put them in chat. We'll get this printed up as a quick bite as well, John.
Okay, yeah, I'll sort that. Let me stop my sharing.
That explains why I couldn't.
Share button broken.
Yeah, what the? How in the world? But what window do I want to share? I better go look before I share it. Let me find that for us. There it is. Okay. So it looks like that. Okay, so we've made some progress. The challenge was get some hardware together. Tell me if you can see this browser window.
Yep.
Okay. And I'm going to make it just a little bit shorter so I can get it out from under my Zoom controls. All right. We've upgraded the Propeller, the driver, matrix driver, to support the P2 cube. This is all 6 panels simultaneously. And thank you, Chip, for spending time with me yesterday and optimizing the code to a really amazing result. In the end, now we handle all panels, all 6 panels of 64 by 64. This is my test setup. And that's the panels wired together, a large supply, so I can drive them at full 8 amps each that I'm driving. This is when they aren't driven as a panel set. I'm driving just one panel, and you can see the data just feeds off to the further panels. My connector is down here at this end. You can see it down here. I'm running a P2 Edge Mini. When we fixed the panel and got the timing correctly, now we can address each of the panels correctly. And what you see is, while our connector's at this end, the 0th panel is out at the far end of the chain, the way that data is driven. And so this is numbering the panels. This is making sure I can draw individually on each panel and color each panel individually in the code. So there are routines that do this now. Same thing, based on numbering in the chain, this should be where the panels locate on your cube. This would be the top panel, the bottom panel. And then I just nominated these as those because it's a cube, rotate it any way you want, but that should be how the thing looks. And then what I did is, what happens if we try and scroll text around the sides of the cube? And so I threw a scroller on there real quick. Now, the scrolling code in my driver is just an extremely rough draft. It's not performant in any way. And it's even worse on a large cube like this, on a large set of panels. This is a lot of memory being used, but the net result is it's working. This is drawing at a reasonably nice frame rate. And this is the demo here where we have, the panels are just randomly assigned colors. You can see in my panels, the missing corners, pixels, and things like this. I got some dinged up panels, but for these kind of testing, I don't care. I'm just trying to make sure that driver works. So that was that. This is all up the website at the driver. We did some measurement at it, and this was what threw me to what motivated me to talk to Chip yesterday. When I went to 6 panels live instead of 1, I had some really sluggish, really doggy code in there. And we went from 10 microseconds in one loop case down to 715 nanoseconds through just removing that. So dramatic improvements all over. So you can see now, as a 6-panel chain, we are now running, these panels are rated for 20 megahertz. I'm successfully running them at 28.6 megahertz at the current speed. This is bit banging. This is not using streamer or smart pin. Although Chip and I are continually discussing how we actually can do the data stream with smart pins. And so we are still going to play with that. I wanted to get this driver released to everybody first. So you can see the data clock is running at 28.6. In order to do that, I am clocking this guy at 335 megahertz. I run my P2 edges at 335, no heat problems, nothing. They just run nicely. And so I'm doing this so I can determine what the maximum rates of the panels are and see what I can do. What this means then is a single line is taking us, we're putting out an individual line of the 6-panel group across all 6 panels at roughly 69 kilohertz. So 69 kilohertz rate for painting lines on the panels. A single PWM frame, that's 1/16 of a video frame, is we're doing at 2.18 kilohertz or 457.8 microseconds for a full frame. That's the entire, all the pixels of the 6 panels lit. We do 16 frames, PWM frames, so we can get the colors in between red, green, and blue. So we can do yellows and whites and everything else. And so we run a single frame runs at that. You'll notice I say 32 rows at 384 picks across a row. That's because we actually send out the top row and the middle row and continue to descend down in pairs like this. We send out 2 rows at a time. So I'm clocking out 32 rows, but it's actually painting 64 rows. We're doing that with the top half of the panel driven by RGB1, 3 lines of color, and then RGB2, 3 lines of color drives the bottom half of the panel. This is typical for all of our panels so far. So that's how I'm doing that. I really have to measure this because there's a lot of random overheads that can happen as you're trying to paint frames. I am double buffered in the driver. It takes us about 33.3 microseconds to convert 24-bit color full screen buffer, 72 kbytes, into the 16 PWM frames. So technically we can do that. We can write the next PWM frame set while the existing PWM frame is being shown and have the next one ready to go. So the driver at the end of a PWM frame switches to the next one it's given. If it hasn't been given one yet, a PWM frame set, then it just repaints the current one. So at the end of every PWM frame set, it will look for another one and just paint that one instead of the first one it had. So it should be switching automatically. This is what we're seeing. This is a single PWM frame. And you see me going 0 to 31 on the address lines here. And you see me doing a line, a line, a line, a line, a line. And each one of these then is the 384 pixels. But we have the top half color and the bottom half color. So that's what we're seeing here. So RGB1, RGB2. This is the clock, the pixel clock, and this is the latch enable and the output enable for the panels. That's how that works. Then we go to a single PWM row, and now you're seeing me using one address value for one row. They go from 0 to 31. And here again, you're seeing RGB1 and RGB2. So top row and then middle row of the panel, the clock of the data, the latch and output enable are here. And then we switch addresses during the output enable period. And so that's how these panels work. And so here's what we're running. I wanted to show you this because we're actually calculating the line rate. It takes us this period right here, 715 nanoseconds, to pull in the next 2 lines from hub-RAM to cog-RAM. And so I'm pulling in the data and then streaming the data out and pulling in data, streaming out. So what this means is that this row plus the 17 divided by 2 will actually give us the actual row rate. And so that's what I'm doing down here with this math. And so that's how we derive the actual row rates that you see right here. I just took the long one, the short one, added the 2 together and divided by 2, essentially. All of this code has been released last night as of version 0.90. It's going to become 1.00 once I get the multi-panels working for those that have to be configured. Configuring multiple panels in a chain, the 64 by 64 panels that we have today do not require configuration. The panels that do require configuration require me to on power up, send a serial stream out and then latch it into the latches that runs configuration for the driver chips on the panels. And doing that for one panel is easy, that's working. Doing it for multiple panels in a chain turns out to be a bit problematic and a bit mysterious to everybody in the other processor worlds, like the Arduino world and things like that. They're all having problems with it. It's a mystery, and there's 2 or 3 guys that understand it. I've been following their code and chasing down that code, and I still don't have mine working. I have a couple more ideas, so I'm not done yet. But anyway, multi-panel for those that require configuration, not yet working. And we're now moving fast enough to 28 megahertz that I kind of overran these guys. And so I got to detune it for that panel. And so I have to put in a special code that adjusts the weight states for that. I haven't done that yet with this release. So you probably see a 9.1 come out that'll get this panel back on the air. In the end, when I get multi-panel support for these working, I'll bump this up to 1.0. So pretty much that's the news. The latest driver is now in the P2 OBEX as of today. And this is the code. And I'll keep updating this with notes of what's the latest news. And I'll publish this information to the P2 Cube thread today. And that's all I have for an update. Are there any questions?
I have something to say.
Okay, please.
what we should do is we can use the streamer to output those byte streams along, and then use a smart pin to do the clock generation. But
Okay.
it would make a nice little quick byte for Ken to set up that would show, because what we could do is we could capture that with another cog streamer. We could capture all the activity and then show it in a logic analyzer display through debug, so that we could actually have like a little test bench. So, you know, with some little example code, so that people could more easily, without having to visualize so much in their brain, they could actually try out, you know, they could write their own little streamer code and coordinate it with clocking smart pins, and actually see the result captured on their display.
Oh, nice.
On their host machine, just to help out with development. Because when you can see what it's actually doing, it takes all the mystery out of it. Otherwise, if you just see a couple lines of code that starts up the streamer, and then await XFI for, you know, wait for the streamer done, the action's completely not in the code. It's all in the streamer.
Right.
So we need some way to kind of visualize, actually capture what's going on with the pins. Then it takes the mystery out of it, and it's very easy to get a handle on. And we have the debug displays to do that. We just have to have a little thing that can capture some activity.
Right. And we don't have to, in that case, you don't have to run it at performance numbers, and you can run smaller amounts of data, so you can really practice developing good streamer technique.
Yeah, because once if we get this thing working with the streamer, we're going to be able to place the clock at any phase relative to the data.
Yeah, that's perfect. That's going to be a lot of fun.
Yeah, it shouldn't take that long to get working, but we do need like a little test bench for that. And I can just make a program that runs in a cog that opens up a debug display, and then maybe looks for some event, and then just captures some data lines and then shows them.
Right.
You know, captures some pin inputs and shows them.
That's going to be fun to do. All right. Thank you. And that's my update for that.
Thanks,
Stephen.
Yes.
Stephen.
I can hear you.
Do you hear me? Okay. Minor question. When you having problem with the configuration of the chipsets, all the chipsets are hard to configure, or the first one in the chain is easy and the other ones are hard to configure because you can't be sure all the bits are passing through the chipsets to the next connector?
No, let me show you what I do. I have a logic analyzer. And yes, you're absolutely right. There are a number of reasons for why it's hard to configure. My latest problem is this, though. The 6126, FM6126A is being particularly problematic because it doesn't enable the output port until it's configured. And so when you have multiple panels in a chain, when you attach a logic analyzer to the input of the chain and the output of the chain, and you watch what signals are transferring, you'll see that until the first panel is configured, the second panel can't see data. And so in the end, I have to configure 1, configure 2, configure 3, configure 4. I think I'm going to have to do it that way. So that's my next experiment. What some of the coders were thinking was they could develop the entire chain for all the panels and send it out once and latch it. That doesn't seem to be solving anything. And so what it probably means is that I have to do multiple configuration passes until all the panels are configured. That's my current hypothesis. Got to prove it, though. Does that make sense?
Yes, because what Chip did said about using a streamer to snoop at the bus and look what the bits are passing through, you can use another streamer at the output of the next connector to see how the bits are reaching to the next chipset.
Oh,
so
yes, of course.
You can follow. Yes, and it makes a lot of sense if you assembly a whole configuration for 3 or for 4 or 6 panels and send that configuration as a bunch. But I believe you need to wait a little when you pass from one chipset